Welcome to Mrs. Z's Chemistry. As we learned in the last lesson, Niels Bohr lived in the 1800s and early 1900s. As technology advanced and scientists were able to explore the microscopic world, they realized that microscopic particles obey a very different set of rules than do particles in the macroscopic world. Atomic theory, which is just the explanation of an atom and how it works, had to continue changing with each new discovery. Modern atomic theory is based on complicated mathematical descriptions and equations of the atom, and it takes into account that atomic-sized things behave more like waves than particles. So as we learned about waves in our discussion on light and the electromagnetic radiation, electrons also behave like waves, and this is what we'll talk about today. This Schrödinger equation is a linear partial differential equation that describes the wave function or state function of a quantum mechanical system. Pretty complicated. We will not be calculating anything using this equation in this class. In fact, even in my Bachelor's of Chemistry in college, we never used this equation. This equation describes electrons' location by orbitals, which are regions in space where there is a significant probability of finding the electron. In modern atomic theory, protons are still in the nucleus, as we learned before, and electrons orbit around the nucleus, but an atom doesn't look like a solar system the way the Bohr model of the atom seems to show. Instead, the electrons are in orbitals, which are regions of space around the nucleus where the electrons can be found 90% of the time. Each orbital can hold a maximum of only 2 electrons. The energy levels we discussed in the Bohr model of the atom have subshells, and the energy levels in wave mechanics have sub-energy levels. These subshells have been labeled with letters S, P, D, and F. These subshells increase in the amount of energy as they are listed here. S is the lowest, then P has a greater amount of energy than S, and D has a greater amount of energy than P and S, and F has the greatest amount of energy. Each subshell has a distinct shape. The S subshell is spherical in shape. Each energy level has an S subshell, only one S orbital, and each one is larger in diameter than the previous energy level. Here's another image of the S subshell. The distance away from the nucleus of each subshell is measured in picometers. This is a probability graph. Each dot represents where the electron was for a brief moment in time. You can see that the electron spent most of its time in a spherical shape surrounding the nucleus. The P subshell has a dumbbell shape. There are 3 p orbitals in the p subshell. Since each p orbital can only hold 2 electrons, that means the maximum number of electrons the p subshell can hold is 6. The D subshell has this 4-leaf clover shape. There are 5 d orbitals in the D subshell, meaning the maximum number of electrons the D subshell can hold is 10. The F subshell has these funky shapes. There are 7 F orbitals in the F subshell, with a maximum number of electrons the F subshell can hold being 14. Here's what the orbitals look like with them stacked on each other in the atom. So here you have the nucleus at the very center, and then we have the 1s subshell. We can hold 2 electrons in there. In this theory, the electrons are not just orbiting around on the circumference of this shape, but in fact the electrons are moving all around inside the shape. Then here's the 2s subshell, and it can hold 2 more electrons. After that, still within the second energy level, we have the P-shaped dumbbell-shaped orbitals. There's one of them, and then here's another one, and then here's another one. And in each one of these shapes, you can hold 2 more electrons. So that's 6 more electrons that can be held. Then after that would come the 3s subshell, which is this larger circle. We've got 2 more electrons somewhere inside this region of space. We could keep going. The next step would be the 3p dumbbell shape, so larger P-shaped or dumbbell-shaped orbitals sitting up here kind of like this. And then after that, we would draw the 4s subshell, which would be even a larger circle. And then after that comes the D subshell, which is much harder to draw in a 2D flat surface like this, so I will not attempt that. This diagram shows the relative energy levels of the different subshells. Each line represents one orbital that could hold up to 2 electrons. Here at the very bottom is the 1s subshell. Then, with higher energy comes the second energy level, split up into 2 subshells, the 2s, then the 3 orbitals for the 2p subshell. After that comes the third energy level, which has the 3s orbital as well as the 3p orbitals. Then we have, you can see that the 4s subshell is a little bit lower than the 3d subshell. So we actually fill electrons here first, and then we go back and fill the first section of the d orbitals. It's a good idea to color your periodic table like this. You can box in, even lightly shade these 4 different sections. We have the 2s subshell right here, with helium being an s electron as well. You can label the sides as 1s, 2s, 3s, 4s, and so forth. The large number here represents what row on the periodic table. Then we have, in a separate color, our P block. There's no 1P, but it starts with 2P in the second row on the periodic table, and then 3P, and so forth. You can label on the side there. Then comes the D block in another color, and that's this section right here. There is no 1 or 2D, but it starts with 3D, even though it's in the 4th shell, or 4th energy row. Then the F block is down here, and this one starts with 4F. There's no 1, 2, or 3F, or 6 or 7F at the moment. We have 4F and 5F. Since most atoms have many electrons, with each electron being in a specific location, we need to learn the electron configuration of the atoms. This is similar to learning the address of the electrons. The number of available subshells depends on the shell that is being filled. In the first energy level, or n equals 1, we have an s subshell. In the second energy level, we have an s subshell and a p subshell. In the third energy level, we have s, p, and d subshells, and so on. The first step, we have the shell, so that is a number 1 through 7 corresponding to the row on the periodic table. Then we're going to use a subshell, any one of the 4 letters, and then we will indicate with a superscript, kind of like an exponent, the number of electrons in the subshell. So it looks like this. This large number here in blue is the number that corresponds to the row number or shell number or energy level, 1 through 7. Then we have a lowercase letter that represents what subshell we are in, with the possibilities of being S, P, D, and F. And then the superscript or exponent number, looking number, has the number of electrons that are in that subshell. For S, it's either going to be a 1 or a 2. You cannot have more electrons in an S subshell than 2. For the P subshell, because there are 3 orbitals in the P subshell, we could have up to 6, 1 through 6. In the D subshell, there are 5 orbitals, so we could have up to 10 electrons in the D subshell. And then because there are 7 orbitals in the F subshell, we can hold up to 14 electrons for the F subshell. These are the steps to writing an electron configuration for any atom. First, you're going to want to find the element on the periodic table, and then figure out what is the period number, which means what is the row number, how many shells are there total, what is the group number, how many valence electrons, what subshells does it have, S, P, D, or F, and what is then the electron configuration. So let's start by writing the electron configuration for hydrogen. Hydrogen has only 1 electron, and it's sitting at the lowest energy level. In the first energy level, that has an S subshell, and there's only 1 electron in it. This is the electron configuration for hydrogen. Helium has a total of 2 electrons, and both of its electrons are in the 1s subshell. So helium would have an electron configuration of 1s2. Next, we have lithium that has 3 electrons. Lithium is going to fill the first 2 electrons in the 1s subshell, and then its third electron in the 2s subshell. So we put only a 1 after the 2s. Here, with our picture, we have the 1s subshell with 2 electrons in it, and then we now have the second subshell with 1 more electron in it. Beryllium has a total of 4 electrons. Its fourth electron is sitting in the 2s subshell. This is beryllium's electron configuration. It's a good idea to get your periodic table out and follow along with me. The next element is boron. It has 5 electrons. Its first 2 electrons are in the first energy level. Its next 2 electrons in the second energy level in the s subshell. Its fifth electron is still in the second energy level, but in the p subshell. And it only has 1 electron in the 2p subshell. So we could draw our first little p-shaped dumbbell looking orbital here. Carbon has 6 electrons, its first 2 electrons in the 1s orbital, then its next 2 in the 2s orbital, and then its last 2 electrons in the 2p orbital. After that comes nitrogen. Nitrogen has a total of 7. So its electron configuration looks like this. Notice that if you were to count up all of the exponents or superscripts that we have listed here, 2 plus 2 plus 3 is 7. All of the superscripts must add up to the total number of electrons that the element has. After nitrogen comes oxygen with 8, total of 8 electrons. 1s2, 2s2, 2p8. Fluorine has a total of 9 electrons. Oops, I did not mean to say 2p8. I meant a 2p4 last time for oxygen. For fluorine, we have 2p5. So we have 1s2, 2s2, and 2p5 for a total of 9 electrons. We now have all 3 of the p dumbbell shape looking orbitals stacked up in our atom. And then for neon, we have 1s2, 2s2, and 2p6. We have now filled the 2p subshell. We're going to have to open up a new energy level in order to write the electron configuration for sodium, which has a total of 11 electrons. The first 2 in the 1s subshell, the next 2 in the 2s subshell, the next 6 in the 2p6 subshell. Then we have the third energy level. It always starts with an s subshell, and we have only 1 electron in the 3s subshell. This is the electron configuration for sodium. See if you can write the electron configurations for each of these atoms before moving on to see the answer. Here is the answer for the electron configurations of phosphorus, calcium, and iron. This is one way to remember the order of the electron configuration. Start at the top of the arrow and slide down. So we start with 1s2. Then you go back to the next arrow and go back to the top and slide down again and read 2s2. Then you go back to the top of the next one and read 2p6, 3s2. Then back to the top, 3p6, 4s2. Back to the top, 3d10, 4p6, 5s2. And you could keep going, and this would be one way to remember the order of the electron configuration for any atom. This image reminds you that the D block starts 1 number behind. So even though this first row of the D block is sitting in the 4th row on the periodic table, we label it as 3D. Then you have 4D, 5D, and 6D. So label this somewhere on your periodic table as well to remind you that the D block starts 1 number behind. The F block is technically sitting in the 6th and 7th rows of the periodic table. If you were to cut the periodic table right here and slide this D block and the P block all the way over to the right, you could insert this F block right into here. So you can see that the F block is technically sitting in row 6 and 7, but it starts labeled as 4F and 5F. There is no 1, 2, 3F or 6, 7F. Write the electron configurations for nickel, molybdenum, and gold. Here are the answers. So if you're looking at something like gold here, you may have gotten confused with when to start the F block. This periodic table actually really helps with that. You can see that we would start by looking at our 1s subshell right here. Then you go back to the beginning of the periodic table and read it left to right. We have 2s2, and then we have 2p6. Then you've got 3s2, 3p6, and then 4s2, 3d10, 4p6. So this can remind you the order of the periodic table, or the order of the electron configuration. 5s2, and then 4d10, and then 5p6. Here's 6s2, and now we can see that the 4f14 fits in right here before we get to 5d10, 6p6, and then 7s2, 5f14, 6d10, and 7p6. So this is a great periodic table to be looking at when you are writing your electron configurations. You can now begin 6.3 in the practice problem set. You'll learn how to write an abbreviated electron configuration in the next lesson.